Hello there and welcome back to the Science Sleepy Minds. You're floating, completely still, in an empty, star-choked void. The stars look distant, older than time, and the blackness between them feels impossibly large. Your body doesn't move, not because you're anchored, but because there's no up, no down, and definitely no floor to land on. This isn't your living room. This is the edge. Or at least, what we think might be the edge. Is there even such a thing? Or does space go on forever, stretching and looping like some kind of cosmic treadmill, where you run and run but never hit a wall? You probably won't survive this thought experiment without a little existential heartburn. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And tell me where you're watching from and what time it is, because nothing makes this channel feel cozier than realising someone's listening at 2:37 AM from a tiny fishing town in Iceland. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. The universe, as far as your sleepy eyes can see, is absurdly large. There's no edge in sight, no cliff to tumble off, no glittering "you are here" sticker. Just stars fading softly into black, and the deeper you stare, the more it seems like the stars themselves are staring back. You're not really floating at the edge of the universe, but you might as well be, because from Earth's little perch in the cosmic suburbs, we're always peering outward, hoping to glimpse what's beyond the curtain. Here's a spoiler: we've never seen a literal edge, not once, and yet humans love imagining one, like there has to be a wall out there somewhere, an end screen, a game over that says, "Thanks for playing Universe Edition." But space doesn't behave the way your brain expects it to. It's not a giant sphere you could fly to the outside of. In fact, there might not even be an outside. That's the first headbender. When you picture space, you probably imagine a big room, right? A black room with stars painted on the inside. But what if space isn't in anything? What if space just is? Now consider this. The observable universe, the part we can see, is about 93 billion light-years across. You didn't mishear that. Even though the universe is only about 13.8 billion years old, we can see galaxies much farther away than 13.8 billion light-years. That's because the universe itself has been expanding while the light has been travelling toward us, stretching the distance like taffy. And here's where things get spicier than your midnight cup ramen. Just because we can't see beyond that 93 billion light-year sphere doesn't mean there's nothing there. That's just the part light has had time to reach us from. Outside it could be anything. More galaxies, more time, maybe another version of you regretting a slightly different life choice, like that second Mountain Dew. Historians still argue whether early astronomers had any concept of an infinite universe. Most ancient cultures believed in domes, heavens, crystal spheres, a place with a top and a bottom. Ancient Egyptians thought the sky was a goddess stretched over the earth like a canopy. The Greeks? They loved their cosmic spheres, layer after layer of glassy shells that rotated predictably. A universe that wrapped neatly around Earth's ego. Then came Copernicus, who yanked us from the centre, Galileo, who pointed his telescope and found moons orbiting other planets, and eventually Newton, who made gravity the main character. But even Newton's universe, vast as it was, still held on to the idea of space being something we move through, a kind of stage for the cosmic play. But Einstein ruined that cosy illusion. Space wasn't just a passive background anymore. With his theory of general relativity, space and time became fluid, dynamic, and tangled up. Mass could bend space. Time could slow down. And, most unsettling of all, space itself could expand. Like literally grow. So now we have to ask, if space is growing, where is it growing into? But that question is like asking what's north of the North Pole. It sounds logical, but it's sneaky nonsense. If space is all there is, there's no outside for it to grow into. It just expands internally, like dough rising. And this is the moment your brain quietly sets itself on fire, because we're trying to fit non-human ideas into a very human brain. We evolved to throw spears at elk, not to model four-dimensional curvature. Now let's say you had a spaceship, a really good one, faster-than-light anti-aging seats, cup holders that never spill, and you decided to fly in one direction, forever. Would you eventually hit a wall, float into a blank nothingness, loop back to your starting point? Nobody knows for sure. We haven't seen a cosmic wall, and so far space doesn't seem to have edges. Galaxies keep appearing in every direction, and the deeper we look, the older and redshiftier they get. But an edge, no hard border, no oops universe ends here sign. But here's the fringe tidbit to tuck under your cosmic pillow. A physicist once proposed the idea that space could have a Mobius-like structure, a one-sided surface. In this model, if you travelled far enough in one direction, you could end up flipped, your left hand becoming your right mirror style, not just looping back, but reversing, like a cosmic Uno card. So does space truly end, or does it just curve, loop, and keep going? The truth is, we're still floating near the shallow end of understanding. We've barely waded into the cosmic pool, and already we're feeling the chill. But don't worry, tonight's journey is just getting started. Next stop, the speed of light, and why that old photon traffic jam is keeping the universe's secrets from you. You drift now, not just through space, but through time. A soft shimmer hangs around every star you see, and somewhere, deep in your sleepy skull, it finally clicks. You're not seeing the universe as it is, you're seeing it as it was. Every point of light is a message from the past, travelling millions, even billions of years to get to your eyeballs. And by the time it arrives, everything might have changed. Galaxies could have collided, stars could have exploded. That bright little speck you're staring at, it might not even exist anymore. Welcome to the visible limit of the cosmos, a boundary not made of walls or fences but of time, and it all comes down to light. Light travels at around 299,792 kilometers per second. That's the fastest anything can move in this universe. No cheating, no shortcuts, no cosmic speed limits to break with a space Ferrari. This is it. And because of that, we only see as far as light's had time to travel since the beginning of everything, about 13.8 billion years ago. But here's the cosmic punchline. The universe has been expanding that whole time. So the farthest galaxies we can see now are actually about 46 billion light years away. Why? Because while their light was on its way here, space itself stretched like a pair of ancient yoga pants. And it hasn't stopped stretching. In fact, it's speeding up. More on that in a few sections. But for now, just know that everything is fleeing from everything else, like an awkward party, where nobody wants to be the last one standing by the snack table. Now here's a fun visual. You shine a flashlight into space. The beam travels forever, unless something blocks it. But even if nothing does, it can only reach so far before time itself runs out. Imagine time as a huge cosmic loaf of bread, and light can only chew through the slices it's had enough years to cross. That distance, that ultimate reach of light since the Big Bang, is what we call the observable universe. It's our own glowing bubble of visibility, not because the rest doesn't exist, but because it hasn't said hello yet. Like neighbours who moved in just after your last birthday and haven't introduced themselves because their driveway is 20 billion years away. Historians still argue whether early astronomers understood this time delay. The ancient Chinese, Greeks and Babylonians saw the stars as fixed, eternal lanterns hanging in a firm sky. They didn't know those points of light were faraway suns, and certainly not that they were delayed broadcasts from the deep past. The idea that we see into time as we look into space didn't really click until modern physics crashed the party. And let's throw in a weird tidbit here. There are places in the universe moving away from us so fast, thanks to space's expansion, that their light will never reach us. No matter how long we wait, those photons will never close the gap. They're on the other side of what's called the cosmic event horizon. It's like they're shouting into a wind that carries their voice backward faster than they can yell forward. Think about that. Entire galaxies exist, right now, that are forever out of our reach. You could fire up your ship, point the nose toward them, and hit max warp and you'd never get there. Not because your ship isn't fast enough, but because the space between is expanding too quickly. It's like walking up the down escalator, only the escalator is also growing longer behind you. But don't panic. Most of the good stuff is still in range. The observable universe contains something like 2 trillion galaxies, each with hundreds of billions of stars. Statistically, there's probably a planet somewhere made entirely of cheese, or one where people sneeze glitter. Infinite possibilities just out of reach. So how big is the whole universe beyond our observable slice? No one knows. It could be hundreds of times larger, or it could be infinite, which, by the way, is a word that physicists use reluctantly, like a secret ingredient they don't want to admit they threw into the stew. Infinite isn't just a lot, it's endless, and endlessness brings weird baggage. If the universe really is infinite, then every possible arrangement of matter should repeat eventually, because there are only so many ways to rearrange particles in a finite volume. That means there could be copies of you, infinitely many. One is watching this video right now, but in a different accent. Another is brushing their teeth with mayonnaise. Weird, but mathematically plausible. But back to the light. Every time you look at the night sky, you're reading the universe's autobiography. Except the chapters are all out of order, and the ink keeps fading as you read. That fuzzy patch in the sky? Maybe it's from 300 million years after the Big Bang. That bright blue star? Maybe only 50 light years away. Just a blink. And the farthest signals. They come from a time before stars even existed. There's something heartbreakingly romantic about that, isn't there? That to look up is to look back. That the stars are not where you see them. They've already moved on. You're staring into cosmic ghost towns, long deserted. So the edge of what we can see is defined not by distance, but by time, which in turn is defined by how long light has been on the road. The result? A sphere centered around Earth, roughly 93 billion light-years across. A glowing snow globe of visibility, floating in something more. And as you float in your quiet mental spaceship, this knowledge sits heavy but soft in your chest. There's more out there than you'll ever see. Vast swathes of reality are invisible, not because they're hidden, but because they haven't arrived. They're too far, too fast, too late. It's like being at a massive, never-ending concert, and you can only hear the bands whose sound checks are close enough to reach your ears. Beyond that, silence. Not emptiness, just songs still in transit. And maybe that's okay. Maybe mystery is the final frontier. The unreachable places are what keep us looking up at all. Next, we'll press our sleepy noses up against the glass and ask, what exactly lies beyond that cosmic horizon? You hover now just behind the curtain of the known, gazing toward that ultimate horizon, the farthest edge of the observable universe. It's not a place with coordinates or a billboard saying, "Welcome to the end." It's a boundary made of time and light, shifting and elusive, like the fog line between dreams and waking. And naturally, your next question bubbles up, a little louder than the rest. What's beyond it? Well, we don't know, but let's pretend we do, because that's where the fun begins. Start by imagining that you're holding a glowing snow globe, Earth dead center, galaxies swirling in every direction. That bubble, 93 billion light-years wide, is all we can observe. Not because it's all that exists, but because light from beyond hasn't reached us yet. It's like we're in the middle of a party, but most of the guests are still stuck in traffic, and their invitations got lost in the mail. Beyond that snow globe, there could be more stars, more galaxies, more space, possibly an infinite amount. But it could also be something stranger, regions where the physics themselves change, where the constants we rely on, like gravity or even the speed of light, decide to get weird. Think of our universe like a patch on an endless quilt. Our patch is cozy, but stitched right next to it, beyond our visible limits, might be patches made of different threads entirely. Places where hydrogen doesn't form, or where time doesn't move in the plight-forward direction you're used to. Now, a mainstream historical detour. Back in the 1920s, Edwin Hubble showed us that galaxies are moving away from us. The farther they are, the faster they fly. This discovery gave rise to the idea of an expanding universe. Suddenly, space wasn't a fixed container. It was more like a baking loaf of raisin bread, with galaxies as raisins. As the dough expands, the raisins all move away from each other, not because they're flying through the dough, but because the dough itself is stretching. And yes, you are now the raisin. Get used to it. But even though Hubble mapped a revolution, we still don't know if this dough ends somewhere. Does the loaf have crust? Is it part of a giant bakery of multiverses? Or does it go on and on, stale and eternal? What lies beyond the observable universe is fundamentally unknowable. Not just because we haven't seen it yet, but because we can't. Light from those regions is permanently out of reach, redshifted into oblivion by the accelerating expansion of space. You could call that space unobservable, but even that feels too neat. The real term physicists use is the unobservable universe, which, if you think about it, is just a fancy way of admitting that it's the cosmic equivalent of here be dragons. But fringe thinkers, ever the dreamers, have come up with all sorts of ideas. One of the quirkiest, that our visible universe might be a tiny pocket, or bubble, inside a much larger multiverse. Like one soap bubble in an endless foam bath of reality. In this model, called eternal inflation, new universes are constantly budding off, each with its own big bang, its own physics, and possibly its own laws of logic. Somewhere out there, in theory, there could be a universe where gravity pushes instead of pulls, or where time loops like a lasso, or scarier yet, a universe where pineapple on pizza is illegal. But closer to home, here's something to roll around your sleep-deprived neurons. Even if the universe is infinite beyond the observable limit, it might be homogeneous. That's a fancy word for mostly the same everywhere. So even if you could see further, it might just be more of the same. Galaxies, stars, voids, rinse, repeat. Not exactly exciting, but very tidy. Still, historians argue whether that idea is truly supported by evidence, or whether it's just comforting symmetry dressed up as science. Some cosmologists say the assumption of homogeneity is a human bias, a desire for neatness where chaos might reign. And this is where things get philosophical, because asking what's beyond might be like an ant on a tennis ball asking what's beyond the curve. The ant only knows what it can walk across. It doesn't see the stadium, the sky, or the kid about to serve an ace. In that sense, we might be crawling on the surface of something vast and incomprehensible, unable to lift our heads. Or worse, we might be inside a finite universe that loops back on itself, so no matter how far you go, you're always right back where you started. But that idea deserves its own lullaby a few sections from now. Here's a sleepy little image to tuck you in with. Imagine standing at the shore of an infinite ocean at night. The horizon glows faintly, but you can't see past it. You know the water stretches beyond your vision, but how far? What kinds of islands lie out there, hidden in fog? Do ships ever return from those distances? or are they simply swallowed by the silence? This is where cosmology starts sounding like poetry, and maybe that's appropriate because we're asking questions the universe hasn't answered yet, and might never. Now for your quirky tidbit of the night. Some scientists have theorized that if the universe is infinite, and matter is randomly distributed, then somewhere out there's a version of Earth where you're exactly the same as you are now, but with one tiny difference. Maybe your phone's battery is at 94% instead of 95%, or you're wearing socks with whales instead of cats. Statistically, infinite space means infinite duplicates and infinite slight variations. So in a sense, you might already be out there, be on the edge. That's not comforting or terrifying. It's just math being weird again. So, does something physical lie beyond the cosmic horizon? Almost certainly. But will we ever see it? Almost certainly not. Because that boundary is baked into the fabric of space-time itself. It's not a wall we can tear down. It's a curtain woven from the laws of nature. And here you are, tucked in behind that curtain, listening for echoes from the other side. But don't worry, we're not done wandering yet. In fact, our next detour gets a little geometric. Ever wondered what shape space actually is? Spoiler, it's probably not a cube. You stretch gently now, adrift in the inky dark, and space stretches with you. Not in the figurative post-yoga way, but literally. The dimensions around you flex and twist, invisible yet real. Lines that should run straight might actually curve. Shapes you trust, squares, triangles, even your own sleepy outline, could subtly warp. Because tonight, we ask a deceptively simple question. What shape is the universe? It sounds like something you'd doodle in a notebook margin. A circle, a sphere, a donut. We'll get to that one, I promise. But this is no child's drawing. The shape of the universe is a serious ongoing debate that bends light, affects time, and might even decide whether space ends or loops forever. Let's start basic. When cosmologists talk about the shape of the universe, they don't mean its borders or outer shell, because as we've whispered about already, there might not be a border. Instead, they mean the geometry of space itself, the way space bends, stretches and wraps around itself. And it mostly boils down to three possibilities: flat, open, or closed. Option 1. Flat. This means the universe follows the rules of regular geometry, the kind you learned in school and immediately forgot. In a flat universe, parallel lines stay parallel. Triangles always add up to 180 degrees. Light travels in straight paths unless bent by gravity. And if you set off in a spaceship in one direction, you'll never loop back around. You'll just go on forever. That's flatness, infinite, straight, and kind of dull, but tidy. Then there's closed. Imagine a giant sphere, a perfectly round universe, curved inward like the surface of a globe. In this scenario, space has positive curvature, like a basketball. Triangles add up to more than 180 degrees, parallel lines eventually meet, and if you keep flying in one direction, you'll end up back where you started. It's the cosmic Pac-Man idea. Travel far enough and you wrap around. But it gets weirder, because in a closed universe there's still no edge, just like on Earth, where you can walk in a straight line forever and never fall off the planet. Space loops, smoothly, seamlessly. The whole thing is finite in volume, but with no borders. Option 3. Open. This is space with negative curvature, like a saddle or a Pringle. Triangles in this geometry add up to less than 180 degrees, parallel lines diverge, and space goes on forever in every direction. Even weirder, the more space expands, the more it wants to keep expanding. It's not just stretching, it's stretching faster. If this sounds suspiciously like cosmic anxiety, you're not wrong. Now here's where your sleepy head starts to throb a little. These three geometries aren't just theories. Scientists actually measure them using the oldest light in the universe, the cosmic microwave background, or CMB. That's the thermal radiation left over from the Big Bang, still glowing faintly in every direction, like the universe's baby picture. By analysing the way this light bends, stretches and ripples, we can infer the shape of the space it travelled through. Think of it as throwing marbles on a surface and watching how they roll. Are they drifting apart, curving back together, or rolling straight? That tells you something about the surface underneath. So what do the measurements say? The best data we have, especially from satellites like WMAP and Planck, suggest that the universe is flat, painfully, boringly, geometrically flat. Not exactly a dramatic twist, but it fits our math pretty well. And yet, it's only flat to the limits we can measure, which is, to be honest, not much. If the universe curves very, very slightly, over distances far beyond our observable bubble, we wouldn't see it. Flatness could just be a local illusion, like thinking the Earth is flat because you're standing in Kansas. Historians still argue whether early cosmologists even understood the question of cosmic shape. Einstein's theory of general relativity cracked the door open. His equations linked the geometry of space to the energy and matter within it. The more stuff in space, the more it curves. That's how gravity works, after all. Mass tells space how to bend, and space tells mass how to move. But even Einstein didn't have all the answers. His own model of the universe assumed a static cosmos, a mistake he later called his greatest blunder. And it wasn't until decades later that physicists started building serious models of a curved or flat universe. Now for a weird little sidetrack, in some fringe models space might have exotic topologies, like being shaped not like a sphere or saddle, but like a torus. That's right, a cosmic donut. In a toroidal universe, space loops in multiple directions. You could fly straight and return from another angle, and depending on the twistiness, you might see ghost images of the same galaxy appearing in different spots on the sky, light that wrapped around space before reaching you. Sadly, we've found no evidence of repeated galaxies, so either space doesn't loop like that, or the universe is simply too big for the loop to be visible from our little patch. Still, this idea of a looping, self-connected universe is hard to shake. It pops up in everything from math papers to sci-fi novels, and honestly, it's got appeal. A looped universe feels less lonely. It has symmetry, closure, a kind of cosmic echo. But don't worry, regardless of shape, the universe has no known edge. That's the part people always get tripped up on. Even in a closed universe, you can't hit a wall, you just loop. In an open or flat universe, space goes on forever, but it's infinite in the way numbers are, not in the way hallways are. Still, the idea of space being flat doesn't mean it's like a sheet of paper. It just means that the rules of Euclidean geometry, remember him? Apply. Triangles behave, circles behave. The universe, for all its chaos, follows some deeply soothing lines. And maybe that's why this matters. Because when everything else, galaxies, time, matter, you, feels like it's rushing toward entropy, it's comforting to know that somewhere out there, the angles still add up. Next, we get metaphysical with the concept of infinity. If space is truly flat and it never ends, what exactly does that mean? You float now on an unmarked path, the stars thinning out behind you. There's no destination in sight, just more space, more black, more distant pinpricks of light. No edge, no loop, no curve, just the infinite stretch. And this is where things get uncomfortably interesting. What if the universe really is infinite? Not very big, not too far to see, but truly mathematically infinite. Let's not sugarcoat it. Your brain isn't built for infinity. It's a slippery concept. Infinity isn't just a really large number. It's a refusal to stop, a staircase without a top step, a map that zooms forever and never blurs. You can imagine it kind of in an abstract sense, but when you try to picture an infinite universe in physical terms, your brain folds like a lawn chair. Still, if current measurements suggest the universe is flat, and if it's flat everywhere, then the simplest explanation is that it might go on forever. No edge, no boundary, just space repeating, stretching, yawning in every direction. And the implications are more than a little wild. First, if the universe is infinite, then so is the amount of stuff inside it. That means infinite stars, infinite galaxies, infinite planets, and yes, infinite versions of you. Not just the funhouse mirror kinds we mentioned earlier, but exact duplicates. Statistically speaking, with enough matter randomly arranged in an infinite universe, every possible combination must occur. Somewhere out there, there's a version of you watching this video with your socks on backwards and a pet squirrel named Todd. Somewhere else, there's a version who never got out of bed today. And somewhere further still, an identical version of you is reading this exact sentence, but sneezed halfway through. This isn't sci-fi, it's just math, applied with uncomfortable precision. The idea is sometimes called the infinite monkey theorem. If you give a monkey a typewriter and infinite time, eventually it'll type the complete works of Shakespeare. Apply that to the cosmos, and the universe starts to look less like a frontier and more like a cosmic rerun. Quirky enough for you? Good. Now, mainstream science has a complicated relationship with the word infinite. In physics, infinity often pops up in equations as a red flag, a sign that the math has broken down or reached a paradox. Some scientists see infinite universe as a useful working model. Others see it as a philosophical cop-out, like muttering, "It's turtles all the way down," and walking away. Historians still argue whether ancient thinkers grasped the idea of a truly infinite cosmos. The Greek philosopher Anaximander, way back in the 6th century BCE, proposed a boundless universe. But Aristotle rejected the idea outright. He couldn't accept something with no edge. To him, the heavens had to be perfect, finite, and neatly wrapped. Infinity, to Aristotle, was messy and dangerous. He wasn't entirely wrong. It wasn't until much later, centuries after telescopes began showing us a sky full of galaxies, that serious thinkers began entertaining the possibility of an infinite universe again. And even now, the debate is far from settled. Here's where the reality check kicks in. We can't observe infinity. We can't measure it. We can only observe our little bubble, our 93 billion light-year snow globe, and extrapolate from what we see. It's like peeking out a porthole on a cruise ship and guessing the size of the ocean. You might be right, but you'll never know. And here's something even more mind-bending. If the universe is infinite, then its history might be infinite too. And that's where we stumble into a paradox or two. How did we ever get to this moment if there were infinite moments before it? Wouldn't the past be so deep that the present could never emerge? These are the kinds of questions that make philosophers gently close their laptops and go stare into a field. So what's a sleepy stargazer to do? Well, if the universe is infinite, it might not just be in space. Time could also be infinite, stretching eternally forward with no final sunset. And when you mix infinite space with infinite time, you get some rather unsettling implications. For example, somewhere, out there, all the atoms in a random region of space might spontaneously assemble into a perfect replica of your bedroom, you included. These are called Boltzmann brains, disembodied conscious observers that emerge randomly from chaos just for a moment before dissolving again. It's as creepy as it sounds, but don't worry. Most physicists don't think Boltzmann brains are likely, even in an infinite universe. If anything, the fact that you have a coherent, ordered, long-lasting reality suggests that you're not one of those temporary chaotic flukes. Probably. Maybe. Let's not think too hard about that right before sleep. Now let's bring it back down to Earth, or at least to scale. Even if the universe is infinite, that doesn't mean you can go infinitely far. The expansion of space and the limitations of light speed create real barriers. There are parts of the universe you'll never reach, never see, never even know about. The infinite might exist, but it's not yours to explore. Still, there's a kind of comfort in the concept. If space is truly infinite, then you are not at the centre, but you are also not on the edge. No one is. Everyone, everywhere is in the middle of something that never ends. And maybe that's the most honest metaphor for existence there is. So is the universe infinite? The best answer we have is maybe. The flatness of space suggests it. Our models allow for it. But it's unprovable in the strictest sense because you can't measure forever. And maybe that's okay. Maybe it's enough to drift inside the mystery, like a boat on an endless sea. You don't need to see the shore to know the ocean is deep. Next, let's unravel one of the greatest cosmic confusions of all time. Was the Big Bang an explosion, or something far, far weirder? You're floating now near the imagined beginning of everything. If such a beginning exists in a universe that's either infinite or endlessly looping, you squint into the distance, trying to picture what the Big Bang looked like, and your brain immediately betrays you with fireworks, explosions, maybe a dramatic cinematic boom. But sorry to burst your perfectly spherical explosion bubble. The Big Bang was not an explosion in space. It was something much stranger, an expansion of space. You've probably heard the story. Around 13.8 billion years ago, the universe began from a single, incredibly dense point. Bang! Galaxies flying outward, stars swirling, atoms doing cartwheels. Except, that's not quite what happened. And the problem isn't you, it's the name. Big Bang sounds like a firecracker. What actually happened is more like the entire fabric of reality started stretching everywhere, all at once. There was no centre, no blast zone, and, here comes the head tilt, there was no outside into which it expanded. Space wasn't growing into emptiness. Emptiness was part of the growth. It's one of the most misunderstood concepts in all of cosmology. Even some early textbooks got it wrong, suggesting the universe was like a ball expanding in a pre-existing space. But in truth, the Big Bang happened everywhere at once, even in the space your body now occupies. It wasn't a fireball in space. It was space itself becoming. Historians still argue whether the term Big Bang helped or hurt public understanding. British astronomer Fred Hoyle actually coined the phrase as an insult. He was pushing an alternate theory, called the steady-state model, and dismissed the idea of a universe bursting into existence with the sarcastic label, Big Bang. Ironically, the name stuck, and here we are, decades later, still imagining a cosmic grenade going off. Now, let's back up, literally. If the universe is expanding today, as proven by Hubble's observations of distant galaxies redshifting away from us, then rewinding that expansion should take us back to a moment when everything was incredibly close together. A hot, dense state. Not a point, as in a location, but condition. A moment when matter, energy, space and time were all blended into a soup of unimaginable intensity. At that point, the laws of physics as we know them break down. Gravity and quantum mechanics, the two pillars of modern science, refuse to cooperate. It's like trying to merge a medieval cookbook with a modern particle collider. It just doesn't work. This is known as the Planck epoch, the first sliver of a second after the beginning, when the universe was smaller than a grain of sand but contained everything. Time itself may have started here, or maybe it didn't. Some theories suggest time could be cyclical, or that before the Big Bang, time didn't even exist in any recognizable form. Go ahead, let that one lull you into an existential nap. Now here's your quirky tidbit of the section. According to one theory, the universe may have bounced rather than banged. In this idea, aptly named the Big Bounce, a previous universe collapsed in on itself, triggering the rebirth of space and time, like a cosmic breath, in and out, forever. This is still speculative, but it's one of several alternatives to the idea of a singular beginning. Still, most mainstream models favour expansion, and what's key here is that the universe didn't explode into space. It expanded with space, which is why, even today, galaxies aren't flying through space like debris from a blast. Instead, space itself is stretching, gently pushing everything farther apart like dots on a balloon inflating in slow motion. Ah, yes, the balloon analogy. You've probably heard this one too. Imagine dots on the surface of a balloon. As it inflates, the dots move away from each other. There's no centre on the surface, no edge, just curvature and motion. In this model, the two-dimensional surface represents our three-dimensional universe. It's not perfect, but it helps visualize how everything can expand from everywhere at once. We'll pop that balloon in the next section, don't worry. Now, the Big Bang also produced the earliest light in the universe, the cosmic microwave background. This faint glow is the cool-down radiation from about 380,000 years after the Big Bang, when the universe became transparent for the first time. Before that, photons were bouncing around like toddlers in a ball pit, too chaotic to escape. But once atoms formed and the universe cooled, light was finally free to move. That light is still travelling, and with sensitive instruments we can detect it today as a faint hiss of microwave energy from every direction. It's not just noise, it's evidence. A time capsule from the early universe, written in the language of temperature variations and subtle fluctuations. So how does the expansion still affect you? Well, right now, the space between you and distant galaxies is growing. Not because those galaxies are flying away in the traditional sense, but because the space itself is expanding between you and them. This is also why the universe doesn't have a traditional centre. Everywhere was the centre. Everywhere is the centre. That includes you, stargazer. But here's something even wilder. As space expands, the light from distant galaxies stretches too. That's called redshift. The farther away something is, the more its light is stretched into longer, redder wavelengths. At extreme distances, the light is so stretched it becomes undetectable, slipping past the reach of our instruments like whispers in a wind tunnel. And if this keeps happening, which, spoiler alert, it is, then one day, all those galaxies will drift so far that their light will never reach us again. The sky will go dark. Future civilizations might never know other galaxies existed. They'll look up and see only their own stars, unaware of the vast cosmic web that once surrounded them. Cosmic loneliness, brought to you by the acceleration of space. But that's a lullaby for another night. Right now, all you need to remember is this. The Big Bang wasn't a bang. It was a beginning. Not in space, but of space. It didn't happen at a point. It happened everywhere, simultaneously. And the echoes of that strange event are still humming softly in the background, in microwaves, in starlight, in the way galaxies flee like shy party guests avoiding small talk. So next time someone asks you what caused the Big Bang, smile politely and say, "No one knows, but it definitely wasn't a boom." Next up, we'll inflate that cosmic balloon and gently deflate the popular analogies that come with it. You're holding a balloon now, not a festive one. No birthday print, no helium, no string trailing down to your wrist. Just a plain, unassuming, semi-transparent sphere. And this balloon, as you've probably guessed, is not for parties. It's for pondering the nature of the universe, You've likely heard this one before. Imagine the universe like a balloon. The surface represents space. As the balloon inflates, the galaxies on the surface move apart, not because they're flying through space, but because space itself is expanding. It's a handy image. It's taught in classrooms, whispered in YouTube explainers, and drawn on chalkboards with squeaky enthusiasm. But as you cradle this mental balloon, your fingers begin to feel the tension in its surface, the flaws in the analogy. Because yes, the balloon helps, but it also lies a little. Let's float through it together. In the balloon model, the two-dimensional surface represents a three-dimensional universe. No center, no edge, just a curved surface where every point moves away from every other point as the balloon inflates. From the perspective of any single point, it looks like everything else is receding. And that's exactly what we observe when we peer out into the cosmos. You, Earth, this little corner of the Milky Way, everything appears to be moving away from everything else. It's not personal. It's just how the universe is growing. So far, so good. The balloon captures that basic truth. But here comes the first wrinkle. The balloon has a center. It's the air inside. But in the analogy, that center is not part of the surface. It exists in a higher dimension. Our universe, if it's truly three-dimensional and unbounded, wouldn't have a center at all. The center of the expansion isn't a location in space. It's everywhere. It's you. It's your neighbor. It's the distant quasar blinking quietly 12 billion light years away. The balloon analogy also sneaks in the idea of an outside. You imagine the balloon in a room, right? Surrounded by air floating near the ceiling, maybe brushing a cat's whiskers. But the real universe doesn't sit inside something. There's no external space it's expanding into. Space itself is all there is. The balloon gives you the illusion that there's a bigger stage we can't see, and that's deeply misleading. Historians still argue whether early cosmologists even recognized this limitation. In the early 20th century, before general relativity caught fire, many models of the universe did imagine an explosion into space. Some drawings from that time literally depict the universe like a bomb in an open void, galaxies flinging outward like shrapnel. Understandable, but wrong. Now here's a delightful fringe tidbit. Some speculative theories propose that our universe might be the three-dimensional surface of a four-dimensional hypersphere. Think of it like this. If a balloon's surface is two-dimensional and curves in three-dimensional space, then maybe our three-dimensional universe curves through a dimension we can't perceive. In that view, the balloon analogy isn't just a metaphor. It's kind of literal. Sort of. No proof of this exists, of course, but the idea has a dreamy elegance to it. Back to the balloon and its second problem. The dots on the surface, our stand-ins for galaxies, stretch as the balloon inflates. This gives the false impression that galaxies themselves are expanding, but they're not. Gravity holds galaxies and solar systems and you together. It's only the space between gravitationally unbound structures that expands. Picture raisins in rising dough. The raisins stay the same size, but the dough between them increases. So next time you inflate that metaphorical balloon, make sure your dots are glued in place. No squishing allowed. And yet, despite its flaws, the balloon analogy does one very clever thing. It makes the absence of an edge feel natural. When you walk around Earth, you never reach a wall that says end of planet. You just keep going. The same is true for the balloon's surface. There's no edge on a sphere's surface, just continuity. That's the part of the metaphor worth keeping close. So why use the balloon at all? Because your sleepy 3-pound brain needs a hook. We evolved to understand caves and cliffs, not four-dimensional hypersurfaces and expanding vacuum energy. Analogies are scaffolding, and sometimes even bad scaffolding helps you reach the roof. Here's a bonus weird twist. In some models, space might not be expanding at all. Instead, what if we are shrinking? If atomic lengths were gradually getting smaller, the universe would appear to be expanding, when really, we're just measuring everything with shrinking rulers. It's a fringe idea, not widely accepted, but it tickles the imagination. And speaking of ticklish thoughts, let's talk about the weird sensation of motion. You feel stationary, right? But actually, Earth is spinning at over 1,600 kilometers per hour at the equator. It's orbiting the Sun at 30 kilometers per second. Our solar system is orbiting the center of the galaxy at about 220 kilometers per second. And our galaxy, it's speeding toward a mysterious zone known as the Great Attractor at nearly 600 kilometers per second. And on top of all that, space itself is expanding beneath us like a restless mattress. No wonder you feel tired. So what do we do with this metaphorical balloon? Do we pop it or patch it? Maybe we let it float nearby. Not because it's perfectly accurate, but because it gives us a stepping stone. Just remember, there's no rubbery boundary to space, no higher dimension we're inflating into, as far as we know, and no galactic bloat to worry about. The balloon isn't the universe. It's a bedtime story for the part of your brain that still needs shapes, edges, and air to make sense of forever. Now, if space really does stretch like this, could it ever stretch around? Could the universe loop? Keep floating, and we'll chase that idea next. The possibility that space doesn't end, but connects back to itself, like the ultimate cosmic shortcut. You're drifting now with purpose, not just floating aimlessly through expanding space, but gliding in a single direction, straight ahead through a quiet stretch of starless dark. No galaxies in sight, no planetary postcards, just a faint sense that you're going somewhere. And here comes the question that's probably been itching at your sleepy brain. If you kept going, would you ever come back around? Tonight we're chasing a tantalizing possibility. What if the universe loops? Not metaphorically, literally. Like Pac-Man zipping off the right side of the screen only to reappear on the left, or a snake eating its own tail. A cosmos where travelling far enough in one direction might bring you right back to where you started, without ever turning around. Take a breath. It's about to get weird. Let's rewind to what we talked about earlier. Remember those three possible shapes of the universe: flat, open, and closed. The closed universe, the one with positive curvature, like the surface of a sphere, is where this idea of looping gets juicy. In a closed universe, there are no edges, no boundaries. Space bends in on itself, and if you could somehow travel fast enough and far enough in a straight line, you'd eventually return to your starting point. Yes, even if you never change course. It's deeply unintuitive but mathematically sound. A closed universe could be finite in size but unbounded in structure. Like Earth's surface, walk in a straight line forever, and eventually you circle back, but in 3 dimensions. Here's where your geometry teacher returns to haunt you. You remember Euclid? Good old, the angles of a triangle always add up to 180 degrees guy? In a curved universe, Euclid takes a nap. Triangles behave differently. Distances don't scale the way they should, and space, instead of stretching forever, curls back like a smug little cat. Now, you're probably wondering, has anyone tested this? Actually, yes. Cosmologists have spent years looking for signs of spatial looping in the cosmic microwave background, the ancient glow left over from the Big Bang. If space does loop, we might expect to see repeating patterns in the CMB, like matching circles or hot and cold spots, as light travels around the universe more than once before reaching us. So far, though, no repeats. The sky looks unique in every direction, which strongly suggests that if the universe does loop, the loop is much larger than our observable bubble. Historians still argue whether Einstein himself ever embraced the idea of a looping universe. In some of his early models, space was closed and finite, a kind of cosmic sphere, Later, he entertained other options. Like any good physicist, he was open to tweaking his equations to match the data. But the idea of a looping universe never fully vanished from the scientific imagination. Here's your fringe but delightful thought for the evening. There are models of the universe where space loops in multiple dimensions, not just front to back, but side to side, up and down, and even on weird diagonal axes. These are called multiply connected universes. Imagine a three-dimensional version of a video game map, where going out one side doesn't just bring you back, but maybe even flips you, rotates you, or timestamps you. One especially bizarre possibility: if space loops in just the right way, you might one day see your own spaceship approaching from the other direction. It left thousands or billions of years ago, and it's still you, just the long way around. In fact, some early universe models even suggest light itself could wrap around the cosmos. A single photon emitted shortly after the Big Bang might have travelled the full loop of space and arrived here from behind. That's right. Some of the light we see in the night sky might have taken the scenic route, circling the universe once before ending up in your eyes. So why haven't we seen that light clearly duplicated, like a cosmic rerun? Because the universe may simply be too large. Even if it loops, the loop might be on a scale far beyond the observable universe. Imagine standing in a field so vast you can't see the curvature of Earth. It feels flat, but that's just because you're tiny. Same deal with space. Local flatness doesn't prove global infinity. Now, for a bit of gentle sarcasm to keep you grounded, you might be thinking, well, if space loops, shouldn't we be mapping the sky like a Mario Kart track? Sadly, no. While that would make the universe significantly more adorable, we're still stuck with one problem. We can only see a small part of it. Our cosmic neighbourhood is vast, but not vast enough to reveal a full circuit. And speaking of Mario Kart, if space loops, does that mean we're all racing around endlessly? Galaxies lapping each other over billions of years? Not quite. Because while space might loop, the expansion of space complicates things. It's like racing on a track that stretches as you run. Even if the universe curves back on itself, the expansion can be so rapid that it outpaces your ability to return. In other words, you could try to make a full lap of the cosmos, but the lap gets longer as you go. Space is the ultimate cheater in a marathon. Still, there's something soothing about the possibility of cosmic closure. In a universe that loops, nothing is ever truly lost. Light travels long enough, and it finds its way home. Every path leads back to itself, eventually. It feels neat, circular, almost poetic, but not everyone's on board. Some physicists favour a flat or open universe, one that goes on forever in all directions, no looping required. Simpler, they say, more consistent with observations, and maybe they're right. But simplicity isn't always satisfying. There's a comfort in the loop, in the thought that if you left your home galaxy and flew straight for eternity, you wouldn't fall into a void. You'd come back, full circle, different, but home again. And maybe, somewhere out there, light is still doing exactly that, making its long, slow loop through space, whispering back ancient truths from the edge of everywhere. Next, we tumble even deeper into the odd. What if our universe isn't the only one? What if it's just one bubble in an infinite foam bath? You've barely settled into the curve of looping space, and now we're jumping again. This time right off the edge of our universe entirely. Not into empty space, not into more galaxies, but into other universes. Yes, plural. Welcome to the multiverse. It sounds like a word scribbled in the margins of a comic book, or the plot of your favourite movie where 3 versions of the main character team up to punch a space octopus. But this idea that our universe might be just one of countless others isn't just science fiction anymore. It's a serious, if highly speculative, line of inquiry in modern cosmology. And here's the kicker. If the multiverse exists, then asking whether our universe loops or ends might be like asking whether one bubble in a bathtub is round or square. It matters, but only if you ignore the rest of the tub. Let's start with the most popular version: eternal inflation. Remember the Big Bang? The moment when space itself began expanding? Well, some physicists think that this expansion wasn't a one-time event. Instead, it might be happening all the time, in countless places, constantly bubbling off new universes. In this view, our universe is just one pocket of stable space in a much larger inflating megaspace. A wild, ever-growing field where big bangs are popping like popcorn kernels in slow motion, and every one of those bubbles, a universe, possibly with different physics, different dimensions, different versions of reality. Some so alien we couldn't survive a nanosecond inside them, others eerily familiar. You might be thinking, that sounds impossible to test. You're right, it is, for now. These universes would be completely cut off from ours. No contact, no wormhole backdoors, no quantum postcards. The expansion of space between them is so fast that even light can't cross the gap. But still, the math behind eternal inflation falls naturally out of existing theories. It's not something someone dreamed up during a sleepless weekend. It's what happens when you let the equations do their thing, and then follow them past the point where things stop making intuitive sense. Historians still argue whether this marks the edge of science or the beginning of science fiction. There's a real debate in physics about whether untestable theories should count as scientific. Some call it elegant extrapolation, others call it guesswork in a tuxedo. Let's sprinkle in a delightful fringe tidbit here. One version of the multiverse suggests that every quantum event, every moment where something could go multiple ways, actually does. This is the many worlds interpretation of quantum mechanics. According to it, every time you make a choice, the universe splits. You take the job and you don't. You spill the coffee and you don't. Somewhere out there, another version of you is living the outcome you never picked. Somewhere else, you're not watching this video. You're asleep, or underwater, or made entirely of bees. That version of you is very busy. And here's where it gets deliciously absurd. If space is infinite and the multiverse is real, then everything that can happen does happen, somewhere. Every novel ever written, every thought ever thunk, all playing out in some pocket of reality over and over and over. Pause for a breath, let that one wash over you. But here's the reality check. There's no current way to prove any of this, not directly. These other universes, if they exist, are outside our observational reach. The cosmic horizon we talked about earlier? It's like being stuck in one room of a mansion the size of infinity. The doors are locked. You hear muffled sounds, maybe, but you can't peek into the other rooms. Still, some cosmologists are trying to find indirect clues. One idea? If another universe ever collided with ours during the early moments of expansion, it might have left a scar, a kind of cosmic bruise on the microwave background. So far, no convincing bruises, but people are definitely looking. Now let's dip into another flavour of the multiverse, the string theory landscape. In string theory, the building blocks of reality aren't particles, but vibrating strings of energy. And the way these strings vibrate depends on the shape of extra dimensions. Yes, dimensions beyond the 3 we move through, and the 1 we age in. There are a lot of ways these extra dimensions could be shaped, like 10 to the power of 100,000 kinds of ways. That's a 1 followed by more zeros than there are atoms in the observable universe. Each of those combinations could describe a different universe with different laws of physics. Some would be dead and dark, others might have stars made of dark matter, and somewhere in this landscape of possibilities is the version that matches our universe. Lucky us. Critics call this a cosmic cop-out. If everything is possible, they say, then nothing is predictive, and fair enough. The multiverse stretches the definition of science to its limits, but it also offers a potential answer to the age-old question: why is our universe so perfectly tuned for life? Maybe it's not tuned at all. Maybe we're just in the one that worked. Like a fish marvelling at how perfectly water supports its gills. Of course it does. Otherwise you wouldn't be here to notice. Now for a bedtime visual, picture yourself drifting between universes, bubble to bubble, each one containing a different sky, a different physics textbook, a different you. Some are lit with 2 suns, others are heavy with red oceans or humming with electric clouds. Some contain no matter at all, just empty rules, swirling pointlessly. And in all of them, time moves forward, or sideways, or loops, like a snake curled into a question mark. So what does the multiverse mean for our original question? Does space end or loop? Well, if the multiverse is real, then our universe may be just one kind of space, with its own rules and boundaries. It might loop, it might stretch infinitely, it might even end, but only from the inside. Beyond it, not a wall, just more. Other spaces, other stories. And the biggest twist? You'll probably never know for sure, which might be the most wonderfully frustrating truth of all. Next time we'll rein things back in a bit and ask, is the whole idea of space having an edge just a flawed way of thinking? You're drifting again, but this time your course doesn't take you outward. It turns inward, not toward the stars or through the void, but into the corners of your own assumptions. Because before you chase more galaxies, before you loop around space or pop into parallel realities, there's a deceptively simple question hanging heavy in the dark. Is the edge of space even a thing? Go ahead, picture it, the edge. What do you see? Maybe you imagine a jagged cliff hanging over nothing. Maybe a glowing boundary of static where atoms blink out. Or maybe you picture some kind of wall, huge, cold, ancient, riddled with strange graffiti left by civilizations that got there first. Whatever your version is, it probably involves some final line where space just stops. But here's the uncomfortable truth. That idea, the edge, is probably just you being human. We like edges. We're comforted by endings. You like your roads to have shoulders, your shelves to have bookends, your stories to wrap up. Even infinity, when you try to imagine it, often gets squished into a loop, or a spiral, or something that gives you the illusion of structure. But space, real space, it's not obligated to obey your mental shortcuts. Let's break this down a bit. Space, as defined by physics, is not a thing so much as a relationship. It's the scaffolding that lets distances exist, the coordinate system in which matter and energy can interact. You don't move through space the way a fish swims through water. Space isn't made of something, it's the arena, and in some models it is the game. So asking where does space end might be like asking where does up stop being up. It's a question that contains its own confusion. You're looking for an edge in a thing that, by its very structure, doesn't require one. Historically, this tripped up quite a few big thinkers. For centuries, philosophers and astronomers assumed the universe must have an edge. After all, Earth had edges. The oceans, they thought, had edges. Why not the sky? One of the earliest recorded arguments against this came from Lucretius, a Roman poet and philosopher in the 1st century BCE. He imagined throwing a spear into the edge of the universe. What happens? Does it hit something? Then the universe has a boundary. Does it keep flying? Then space continues. Either way, he said, there can't be an edge. Something must always lie beyond. Historians still argue whether Lucretius was being literal or poetic, but his logic still holds up better than some modern science fiction. Fast forward a few centuries to Newton, who envisioned space as a vast, empty container. To him, the universe could have an edge, but if it did, there'd still be absolute space beyond it. Empty, infinite, just waiting. like a cosmic attic full of nothing. Einstein would eventually blow that idea to shreds with general relativity, showing that space isn't fixed. It can bend, twist, warp around mass, expand, even end, not with a wall, but with a change in geometry. And that's key. Space doesn't need an edge to be finite. Imagine the surface of a sphere again. Not the balloon itself, just the two-dimensional surface. It's finite. You can walk around it, eventually returning to where you started. But there's no edge to fall off. It's bounded, but not bordered. Now extrapolate that into 3 dimensions, and you've got a universe that curves in on itself. No walls, no limits, just looping geometry. This is where the idea of topology comes in. That's the branch of mathematics that studies properties that stay the same even when things are stretched or bent. And it's full of wild, mind-bending possibilities, like spaces shaped like tori, donuts, Klein bottles, don't ask, or dodecahedrons, we will ask later. These shapes can be finite but edgeless, and some cosmologists think our universe might be one of them, meaning space could wrap, twist, fold, or interconnect in ways that defy your GPS, but still leave you feeling like you're going in a straight line. So why do we keep imagining edges? Part of it might be the way our senses evolved. You live in a world of objects and surfaces. You can walk to the edge of a field, the edge of a bed, the edge of a screen. Your brain craves boundaries because boundaries are useful. They define safety. They tell you where to stop walking before you trip over something important. But the cosmos doesn't care about your ancient monkey brain need for boundaries, and the idea of an edge of space might just be a projection, like painting walls on fog. Here's your fringe science snack for the section. Some researchers once proposed the universe might be like a cellular automaton, a vast grid of discrete bits like pixels in a game. In such a model, the edge of space could be where the grid ends. But if true, that would imply the universe is digital at its deepest level. Not continuous, but pixelated. No proof yet, but it's a strangely satisfying image. Reality, just a few zooms away from showing the grid. Back in the mainstream though, we have to admit, there's no observational evidence for an edge, no wall, no drop-off, no final curtain. The universe just keeps going, at least as far as light has shown us. But what if, just what if, there were an edge? What would it look like? Would time stop? Would atoms vanish? Would there be a shimmer, a membrane, a change in the laws of physics? We don't know, and we might never know, because if the edge is truly beyond our observable universe, it's cut off from us not just by distance, but by the laws of causality. No light from beyond, no message in a bottle. No, sorry, you've reached the end of reality pop-up. So maybe it's best to stop looking for edges altogether. Maybe the universe is edgeless not because it's infinite, but because it's self-contained. Like a story that wraps around itself. Like a thought that leads you right back to the beginning. Space might not need a beyond. It might just be what it is. Complete, curved, expanding, and endless, not in length, but in possibility. And speaking of bending boundaries, next we'll slip through the folds of space itself and visit a place even weirder, the wormhole. So far you've been gliding forward, gently, patiently, through cosmic distances, like a passenger on a luxury cruise ship with no itinerary. But now you're stepping off the gangplank and into something a little riskier. Because tonight we're slipping through the folds of space itself. No more slow expansion, no more wondering about the edge. We're diving headfirst into the tantalizing, terrifying, possibly fictional world of wormholes. Yes, wormholes. Space's cheat codes. The cosmic backdoors that let you skip the loading screen. You've seen them in movies, probably imagined one opening up behind your laundry basket. But what are they really? Could they exist? And if so, where would they go? Let's crack open this theoretical trapdoor. First things first, a wormhole is a hypothetical tunnel through space-time. Think of the universe as a giant piece of paper. Now draw two dots far apart. Normally, you'd have to travel across the paper from A to B. But what if you folded the paper until the two dots touched, then poked a hole through? Boom, shortcut. Wormholes are that hole. They don't just connect 2 points in space, but potentially 2 points in space-time. That means a wormhole might let you travel vast cosmic distances instantly, or maybe even jump across time itself, which sounds like cheating, because it is. But here's the catch. Wormholes are purely theoretical. They do pop out of the math though, specifically Einstein's equations of general relativity. In 1935, Einstein and physicist Nathan Rosen proposed what's now called an Einstein-Rosen bridge, a sort of tunnel linking two black holes, a cosmic bridge, sort of like the universe trying to connect its own dots. But there's a problem. There's always a problem. These wormholes, as described by standard physics, are unstable, like hilariously unstable. If you tried to enter one, it would collapse faster than a house of cards in a wind tunnel. The very moment matter, or even light, entered it, the structure would pinch shut. So unless you're faster than physics itself, spoiler, you're not, the shortcut slams shut before you can take a step. Enter exotic matter. To hold a wormhole open, you'd need a substance with negative energy density. Something that pushes space apart instead of pulling it together like gravity does. And no, we don't have any of that lying around in a lab fridge. But the idea of exotic matter isn't completely fantasy. Some quantum field theories suggest tiny amounts of negative energy can exist in bizarre specific conditions, like the Casimir effect, where two plates in a vacuum attract each other because of suppressed quantum fluctuations. It's real. It's measurable, but it's minuscule. So yes, exotic matter exists in theory. Enough to prop open a wormhole? Not even close. But that hasn't stopped physicists and sci-fi writers from dreaming. Historians still argue whether the idea of wormholes is a distraction or a doorway. Some say it's mathematical decoration, a curiosity with no bearing on reality. Others think it's a signpost, pointing to gaps in our understanding of space-time. Einstein himself thought of them more as curiosities, but modern researchers like Kip Thorne, yes, the guy who consulted on Interstellar, have published serious papers on the plausibility of stable wormholes under the right, wildly theoretical conditions. Now for your fringe tidbit, there's a concept called a traversable wormhole, which is a kind you could theoretically survive. In 1988, Morris and Thorne, yes, that Thorne again, published a paper proposing that if exotic matter could be arranged correctly, you could travel through a wormhole without being crushed, fried, or rearranged into spaghetti. Nice. Even weirder. Some versions of traversable wormholes would let you return before you left. Yes, time travel. If one end of the wormhole experiences time dilation, for example by orbiting near a black hole, then time flows differently at each end. Step through one side and you could emerge in the past or the future, depending on which way the clock is spinning. So here's your sleepy philosophical headache. If wormholes allow time travel and time travel allows paradoxes, what's stopping us from using them? That's where the universe politely declines. Many physicists believe the laws of reality protect themselves against paradoxes. This is sometimes called the chronology protection conjecture, a theoretical firewall that keeps causality from breaking down. Essentially, the universe doesn't want you messing with its timeline. You can imagine wormholes, sure, but building one might trigger feedback loops, quantum instabilities, or some unknown law that slams the door before the party even starts. But let's imagine, for one dreamy second, that wormholes do exist, somewhere in the universe, hidden in voids, anchored to black holes, or threaded between galaxies like silent highways, what would it mean? It would mean space doesn't just expand, it folds. It connects in unexpected ways. It has shortcuts. And if it has shortcuts, then distance becomes optional. The edge of space might be closer than we think, not because it ends, but because it curls. The ultimate cosmic prank. You travel 1 billion light years and find yourself right behind your house 5 minutes ago. Of course, if wormholes exist, they're probably rare, or invisible, or tiny, quantum-sized and constantly winking in and out of existence. There's a theory that says space-time is frothy at the Planck scale, full of tiny wormholes flickering like static in the deep structure of the universe. That's called quantum foam. Yes, you're now officially floating in quantum foam. Try not to spill. So what does this mean for our core question? If space ends or loops or folds, then wormholes might be the connectors, the gaps, the side streets on the universal highway. Maybe they're not outside space at all, but inside it. Hidden passages in a building you thought you'd already mapped. But remember, there's no evidence yet. No wormhole sightings, no starships vanishing into little glowing holes, just math and dreams and maybe 1 or 2 suspiciously bent areas of thought. Still, it's comforting in a way. Because if space is vast, then wormholes give us hope. Hope that there's a way to cross the uncrossable, a way to skip the wait, a way home, no matter how far you go. And if gravity can curve space so deeply, what else might it be doing? Next, we explore how the hidden mass of the universe might not only shape space, but trap it, fold it, and make it loop when you least expect it. You've passed through imaginary wormholes and survived. Not bad for someone in slippers. But now, as the hypothetical shortcuts dissolve behind you, you find yourself suspended in a quieter, heavier part of the universe. There's no movement here, not really. Just a weight in the dark, a tension beneath the stars. Because tonight it's gravity's turn, not the kind that tugs your tea off the table, not the kind that ruins your phone when you drop it on the bathroom tiles at 2 a.m. No, this is cosmic gravity, the kind that shapes galaxies, bends light, warps space, and maybe folds the universe into a shape that loops back on itself. So the question is, if gravity can curve space, could it curve it enough to close it? Could it turn the universe into a loop, a sphere, or something stranger? Let's find out. First, gravity isn't a force in the way you think it is, not according to Einstein. He showed us that gravity is what happens when space-time curves in the presence of mass and energy. You're not being pulled to the ground, you're following the straightest possible path through curved space. The classic analogy? A bowling ball on a trampoline. The ball sinks into the surface, and marbles rolling nearby follow curved paths, not because they're being tugged, but because the surface itself is distorted. Gravity is that distortion. Massive objects tell space how to bend. Space tells objects how to move. Now scale that up. Massive galaxies. Bend space. Galaxy clusters. Bend it more. A black hole. Forget it. That's a trampoline with a hole torn straight through. And when you account for all the matter in the universe, gravity isn't just shaping local space. It's sculpting the geometry of the cosmos itself. But here's the twist. Matter doesn't just create gravity, it also determines the shape of space on the largest possible scale. If there's enough matter, enough gravitational pull, space could curve inward, like the surface of a sphere, a closed universe. If there's not enough matter, space might curve outward, like a saddle, an open universe. And if the mass is just right, flat as a cosmic pancake. So scientists ask, what's the actual mass-energy content of the universe? How much stuff is out there? Enough to curve space inward? Or are we floating on a flat sheet? This is where things get weird. Because when astronomers tally up all the visible matter, All the stars, galaxies, gas clouds, space dust and enthusiastic alien karaoke bars, it adds up to only about 5% of the total energy content of the universe. 5%. The rest? A shadow show. Dark matter makes up roughly 27%. It doesn't emit light, doesn't absorb it, doesn't interact with electromagnetism at all. But we know it's there, because we can see its effects. Galaxies spin faster than they should. Gravitational lensing, where light bends around massive objects, is stronger than visible matter alone can explain. It's like watching leaves swirl on an invisible wind. The wind isn't visible, but the effect is undeniable. And then, of course, we have dark energy, the big mystery clouding all of this. It makes up the remaining 68% of the universe's energy budget, and it does the exact opposite of gravity. Instead of pulling things together, dark energy pushes things apart. It's responsible for the accelerating expansion of the universe, which is both fascinating and rude. Back in the day, most scientists assumed the expansion of the universe would slow down over time. Gravity, after all, should be reeling everything back in. But in 1998, two teams discovered something shocking. Distant supernovae were dimmer than expected. The universe wasn't just expanding, it was speeding up. Dark energy was the culprit. And now, instead of a future big crunch where gravity reigns supreme, we may be heading for a big chill. Or worse, a big rip. Historians still argue whether this discovery is the beginning of a new age in cosmology, or just a temporary glitch in our models. We still don't know what dark energy is. A property of space itself? A dynamic field? A misreading of the data? But here's the kicker. When you put it all together, visible matter, dark matter, and dark energy, current observations suggest that the universe is very close to flat, balanced on a cosmic knife's edge, not obviously curved inward or outward, just precisely in between, which seems too perfect, suspiciously perfect. And yet, that's what the data says. Still, we have to ask, what if the data's incomplete? What if we've underestimated the influence of dark matter, or overestimated the push of dark energy? If space is a balancing act, even tiny mismeasurements could tip the whole thing into curvature, and that curvature could be subtle. Imagine a universe so gently curved that it takes trillions of light years for the bend to become noticeable. It would look flat to us, but in reality, space could be curling ever so softly, eventually looping back on itself like a cosmic pretzel you can't taste. Now for your quirky tidbit, some scientists have proposed that dark matter might not be stuff at all, but a misinterpretation of how gravity works at large scales. This idea, known as modified Newtonian dynamics, or MOND, suggests that maybe our equations are just wrong. That gravity behaves differently when it gets really weak. It's controversial. Most physicists still back the dark matter model. But Mon sticks around, like that one friend who keeps showing up to game night with a new theory about aliens. Either way, whether it's invisible particles or broken math, something unseen is shaping the cosmos. And when you follow that hidden hand, you realize something profound. Space isn't just being shaped, it's reacting, expanding, curving, responding to unseen influences, which means the question, does space end, might hinge on a riddle we haven't solved yet. What exactly is filling it? The universe isn't a static box, it's an elastic tapestry woven with threads we can't all see. And gravity, visible or dark, is the needle pulling that fabric tight, twisting it in strange ways. So yes, gravity might be the reason the universe loops, or expands forever, or folds into topologies too weird for textbooks. And next, we leave space behind just for a moment and ask the next impossible question. If space can loop, could time do the same? Time. You feel it every second. Not just ticking clocks and sunrises, but the slow melt of ice in your drink, the The way dust gathers in corners, how your favourite t-shirt fades just a little more every time you wash it. Time is the great unfolding, but tonight, let's get bold. Let's ask the question that makes physicists sweat and philosophers smile into their tea. Could time itself be a loop? We've talked about the shape of space, flat, curved, maybe even twisted like a pretzel at a carnival with questionable hygiene. But space doesn't act alone. It's in a permanent cosmic tango with time, and if space can curve, expand and loop, why not time? Let's drift gently into the possibilities. In everyday life, time feels linear, cause then effect, past, then present, then future. You wake up, you make coffee, you go to work, or you stay in bed and watch sleepy science videos. Respect. But physics? Physics doesn't play by that script. At the deepest level, especially in the equations that govern quantum mechanics and general relativity, time is reversible. The math works just as well forwards as it does backwards. A universe evolving from Big Bang to heat death is just as valid, mathematically, as one running in reverse. Stars reassembling, entropy shrinking, light collapsing back into its sources. So why don't we see time run backward? That's the great mystery of the arrow of time, and the leading theory points to one culprit: entropy. Entropy is the measure of disorder in a system. It's the reason ice melts instead of spontaneously forming in your glass. It's why you can scramble an egg but not unscramble one. The second law of thermodynamics tells us that entropy tends to increase. Always. It's the reason we remember the past but not the future. And the Big Bang. It started with incredibly low entropy. Which is strange. Why would the universe begin in such an ordered state? It's like dropping a deck of cards and finding them land perfectly sorted. Historians still argue whether that initial low entropy was a fluke, a rule, or something deeper. Some theorists think it hints at a cyclical universe, one where time itself doesn't stretch in a single, endless line, but loops, like a cosmic circle. No beginning, no end, just rebirth. Enter the Big Bounce. This theory imagines that the universe doesn't end in heat death or a big crunch, but bounces, collapses inward, then explodes outward again, over and over. Each cycle a new version of time, maybe a new version of physics, maybe even a new version of you. In some models, time resets completely at each bounce. In others, it might carry over subtle traces, like echoes from previous universes, ancient scars buried in the structure of spacetime itself. Patterns we can't yet see, or barely see. Maybe the reason time feels linear is because we're stuck in one loop, reading one paragraph, unable to flip the page. And yes, this gets even stranger. Some solutions to Einstein's equations allow for closed time-like curves. That's just a fancy way of saying time loops, not for the whole universe, but for certain regions of space-time. In theory, if you could enter one, you'd circle back to your own past. These loops are tightly linked to the idea of rotating black holes, wormholes, and other exotic structures. But before you pack your suitcase for 1997, there's a problem. Every time we try to plug one of these time loops into physics, paradoxes pop up. What happens if you go back and stop yourself from going back? What if you create a future that prevents the past from creating that future? These are the classic time travel headaches. And as we mentioned in the last section, many physicists believe the universe has chronology protection. Like a bouncer guarding the timeline, it slams the door on any process that might lead to a paradox. So what does that mean for cosmic time loops? Are they impossible? Not quite. There's a loophole, because of course there is. Some models suggest that time might loop globally, not locally. In other words, instead of people zipping around the timeline like sci-fi tourists, the entire universe might cycle through phases. Repeating. not with identical details, but with repeating structure. Imagine this. A universe expands, ages, slows, collapses, then bounces and begins again. Not a clone of the last universe, but a new one. Like a tree growing, dying, and dropping seeds for the next tree. Time, in this vision, is a spiral, returning, but never quite the same. Now for your quirky tidbit, the ancient Indian concept of kalpas describes the universe cycling through long ages, billions of years each. Creation, preservation, destruction, rebirth, over and over. Sound familiar? It's not modern physics, but it's poetic how close those intuitions sometimes come. And here's where it gets dreamy. If time loops, maybe you've lived this moment before. Maybe you're not just hearing these words for the first time. Maybe they've echoed countless cycles back. You're not just falling asleep to this script tonight. You've fallen asleep to it in universes past. Countless yous, countless nights, always reaching for the same gentle mystery. Comforting? A little. Disturbing? Also yes. But you know what? You're here now, in this loop, and for all its strange possibilities, the moment you're in still feels beautifully linear. You woke up today, you'll drift off tonight. The arrow of time might be a construct, a trick, a geometry of entropy. But it's your trick, and it works just fine. So whether time is a line or a circle, or some unholy spaghetti noodle of causal loops, it's carrying you forward, moment by moment, thought by thought. And in the next moment we return to one of the earliest and most important clues to the universe's shape, light left over from its birth. The cosmic microwave background still whispers to us, if we listen. Let's listen. Shh. You've drifted far now. Your thoughts have stretched and curved and maybe even doubled back on themselves. The stars around you flicker quieter, as if the whole universe is beginning to breathe a little slower. Let's do the same. The sky above you now isn't vast or distant, it's close, warm, a soft blanket of possibility. You don't need to answer all the questions tonight. The loops, the edges, the endlessness, they'll still be here tomorrow, or yesterday, or next time around. Tonight it's enough to rest inside the question. So close your eyes, if you haven't already. Let your breath fall into a rhythm, gentle, steady, the kind of rhythm that even time might envy. Let yourself be small in the best possible way. You're not lost in the universe, you are part of it. A tiny echo in a cosmic pattern, a whisper that may rise again. Good night, you. Sleep well. You're floating deeper now, not through the cold void, but across a warm, invisible sea. It surrounds you in every direction, soft, ancient, and quiet. You can't see it with your eyes, but it's there. Always has been. It's the universe's most enduring whisper, and it's called the cosmic microwave background. CMB for short. This glow, this hum, is the leftover light from the Big Bang itself. And if you want to understand the shape, the age, and maybe even the destiny of the universe, you have to start here, with this soft, nearly uniform radiation that fills the cosmos like forgotten sunlight still echoing through empty halls. Let's turn the lights down and tune in. Roughly 380,000 years after the Big Bang, the universe finally cooled enough for atoms to form. Before that moment, everything was a thick, soupy plasma, so hot that photons couldn't travel far without getting bounced around like drunk pinballs. But once things cooled just enough, atoms, mostly hydrogen, snapped into place. The fog lifted, and light for the first time could travel freely. That light is still travelling. We see it today as a faint glow across the entire sky. Microwave radiation that has cooled and stretched with the expanding universe for nearly 14 billion years. It's not visible to the eye, but with sensitive instruments you can map it. And what you get is, well, surprisingly beautiful. a kind of heat map of the baby universe, mostly smooth with tiny, tiny fluctuations, just a few millionths of a degree hotter or colder in certain patches, and those fluctuations, they're everything. They're the seeds of all structure, of galaxies, of stars, of you. Without those little wobbles in the early universe, matter would never have clumped together. No planets, no sky, no extremely cozy science videos to fall asleep to. Now, why does the CMB matter for our question? Does space end or loop? Because the shape of space leaves fingerprints in this background radiation. Imagine throwing marbles across 3 different floors, one flat, one domed like a sphere, and one warped like a saddle. The paths those marbles take will change depending on the shape of the surface. Same with the light from the early universe. As those ancient photons journeyed toward us, they were bent and shifted by the geometry of space itself. So scientists studied the patterns in the CMB, especially the size and distribution of those fluctuations, and what they found? The universe appears to be flat, or at least very close to flat. The best measurements we have, from missions like COBE, WMAP, and the more recent Planck satellite, show a geometry that's consistent with flat Euclidean space. Not positively curved, not negatively curved, just flat. But don't get too comfortable. Flat doesn't necessarily mean infinite. A space can be flat and still loop, depending on its topology. Imagine a video game screen where the character exits one side and re-enters from the other. The world feels flat to the player, but it's actually wrapped into a loop. In theory, our universe could be like that, just scaled up a bit, or a lot. Historians still argue whether these precise fluctuations are truly cosmic fossils or just statistical noise. Some skeptics wonder if our interpretations are skewed by our assumptions, that we're reading the patterns the way we want to read them. But the CMB remains one of the most powerful tools we have for peering into the structure of space itself. And now for your delightfully odd tidbit of the night. In 2003, researchers thought they spotted something strange in the CMB, a large cold spot, unusually empty. Some speculated it could be evidence of a collision between universes, like our universe brushing up against another bubble in the multiverse. Yes, seriously. Others argued it was just a statistical fluke, or a giant void in space, or even in one fringe paper a sign of the universe's boundary, the edge itself peeking through. Spooky. No definitive answer yet, but that cold spot is still out there, chilling like an unsolved riddle on the sky. So, what is the CMB telling us? First, it tells us the universe had a beginning, a hot, dense moment that expanded and cooled. Second, it tells us the universe is nearly the same in every direction, isotropic, which means there's no privileged spot, no center. Everywhere looks mostly like everywhere else. And third, it hints at the shape of the universe. And that shape, so far it looks flat. But as always, there's a wrinkle. Just because space looks flat doesn't mean it doesn't loop. Some of the most fascinating topologies, like the 3 torus, allow for a flat universe that still curls around on itself in 3 dimensions. And here's where the CMB becomes a bit of a detective tool. If the universe does loop, and if it's small enough, we should see repeating patterns in the CMB, duplicated hot and cold spots from light that's wrapped around the cosmos and reached us from multiple paths. Have we seen these repeats? Not really. Some early claims popped up, but nothing conclusive. If the universe does loop, the loop is likely too large for us to detect, just beyond the limits of the observable universe, like standing in the middle of a vast field and trying to see its curvature with just your toes and a ruler. Still, cosmologists haven't stopped looking. The CMB remains our best clue, a sky-wide record of the universe's first visible moment. A baby photo stretched by time, cradled in geometry, and you, drifting through this quiet bath of ancient photons, are part of that record. Every atom in your body once danced in that hot plasma. You're built from the echoes of the CMB. So, does space end? The microwave background doesn't say for sure, but it hints that space has no edge, that it's either infinite or curved so gently we'll never see the full circle. And in the next chapter we lean into that possibility, deep into the strange geometries the universe might be hiding. One of them, a dodecahedron. Yes, a 12-faced cosmic die. Let's roll it and see what happens. You're still gliding through the dark, silent ocean of the cosmic microwave background. But up ahead, something strange begins to take shape. Not a star, not a planet, not even a galaxy. It's a shape, a structure, suspended in nothingness, rotating slowly, edges glowing faintly with mathematical possibility. It's a dodecahedron, a 12-faced polyhedron, each face a perfect pentagon. A shape you probably haven't thought about since that one time you rolled a natural 20 in a tabletop game. But tonight, it might just hold the key to one of the strangest theories about the shape of the universe. This is the dodecahedral space hypothesis, a real, if speculative, scientific proposal suggesting that the entire universe might be finite, edgeless, and shaped like a multi-connected dodecahedron. Sounds like a geometry teacher's fever dream, but let's break it down slowly. The idea was first proposed in the early 2000s by French cosmologist Jean-Pierre Luminet and colleagues. They weren't just being weird for the sake of weird. They were responding to something curious. Anomalies in the cosmic microwave background we talked about last time. Specifically, a lack of large-scale fluctuations in the CMB, unexpectedly low variations in temperature across the biggest angular distances. This low quadrupole effect, as it's called, could just be a fluke, cosmic randomness. But Luminet and his team wondered, what if it was a clue? What if the universe was too small to support fluctuations on those large scales? What if space, instead of being infinite and flat, was finite and tightly wrapped, like a dodecahedron with identifications, where each face is connected to its opposite with a twist? Let's pause and let that swirl for a second. Imagine living inside a room shaped like a dodecahedron. Now imagine that if you exit through one pentagonal wall, you re-enter from the opposite one. Not just re-enter, but come back rotated by 36 degrees. It's like a funhouse maze where every door leads back into the same room, but from a slightly different angle. That's what this model proposes. The universe is spatially finite, like the surface of a sphere. But in this case, it's not the surface of anything. It's three-dimensional space itself, shaped like a looping dodecahedron. You might wonder, why a dodecahedron? Why not a cube, or a nice friendly torus? Good question. Turns out the dodecahedron is one of the few regular polyhedra that can tile a three-dimensional space in this complex multiply-connected way. It also has a symmetry that naturally suppresses large-scale fluctuations. So it's not just pretty, it's functional. If space is looped this way, light can travel multiple paths and even overlap itself, creating matching circles in the sky. Patterns that, theoretically, we could detect. And yes, people have looked. Researchers have scanned the CMB for circles in the sky, identical temperature patterns that would suggest light has wrapped around the universe and met itself. So far, nothing conclusive, but the search continues. Historians still argue whether Plato would have loved this idea or hated it. The dodecahedron in his time was considered the shape of the heavens, an object so sacred it was said to represent the entire universe. Maybe he was onto something, or maybe he was just throwing sacred geometry at the wall and hoping it stuck. Either way, the idea has never fully left us. Let's roll in a quirky tidbit for tonight. The dodecahedral universe wasn't the only polyhedral model proposed. Other topologists have played with shapes like the Poincaré dodecahedral space, a particularly elegant three-dimensional manifold that loops and twists in truly bizarre ways. It's hard to visualize unless you have 4 spatial dimensions lying around, but the math checks out. It's like Escher took over cosmology and no one noticed. So what would it mean to live in a dodecahedral universe? Well, for starters, you could, hypothetically, see multiple copies of the same galaxy, scattered across the sky, if light has had time to loop around space and reach us from different paths. That would be trippy. You'd see the Milky Way over there, and again, slightly rotated over there. Ghost galaxies, cosmic déjà vu. In reality though, the distances required are so vast that any duplicates would be far beyond the observable universe. And if the universe is just slightly larger than what we can see, the looping pattern might be hidden forever. Like being inside a mirrored room so big, the reflections never return. Still, the concept sticks. There's something about the idea of a universe with closure. Not in a philosophical sense, but a topological one. A space where you can loop forever, where the sky isn't infinite but beautifully folded. No edges, no boundaries, just repetition, variation, and that weird feeling that you've been here before. Because maybe you have. Depending on how space is shaped, light and time and matter might repeat in subtle ways. The dodecahedral model isn't just a gimmick, it's a legitimate candidate in the hunt for the universe's true form. And it reminds us that we shouldn't assume space is simple just because it looks flat. After all, your bedsheets look flat when you're lying in them. That doesn't mean the Earth is. Now, of course, this model is still speculative. The mainstream consensus still leans toward a flat, infinite universe. But the data isn't perfect, and anomalies in the CMB, if they hold up, could hint at something more complex, something polyhedral, something strange. So where does that leave us? Well, like any good mystery, it leaves us watching the sky, waiting for matching circles, repeated signals, subtle rotations in distant galaxies, the fingerprints of a geometry too elegant to ignore. And maybe, just maybe, we live in a universe that isn't flat or endless, but looped in 12 symmetrical directions, like a cosmic dice game that never ends. Next up, we take this weirdness a step further. What if everything, space, time, you, isn't even real in the way you think? What if the universe is a hologram? You've flown through dodecahedrons, toyed with loops, danced on curved surfaces, and stared into the endless black asking if space ends or just folds in on itself. But now you float in front of something far stranger, a question that peels away the very idea of depth, volume, and realness. What if the universe isn't vast at all? What if it's a hologram? No, not like a shimmering sci-fi projection from a droid. We're not talking Princess Leia beaming in over a chessboard. This is a serious, fascinating, and still debated scientific idea, the holographic principle. The short version: everything you experience in 3 dimensions, including time, might actually be encoded on a distant 2-dimensional surface, just like a hologram. All of reality might be a projection, the depth and motion you feel no more real than the illusion of 3D and a holographic sticker on your high school math binder. Let's unpack this with slightly fewer lasers. This idea first emerged from one of the most extreme environments in the universe: black holes. In the 1970s, physicist Jacob Bekenstein proposed something wild: that the entropy, remember that from earlier, of a black hole isn't proportional to its volume, but to the area of its event horizon, the surface beyond which nothing escapes. Stephen Hawking later showed that black holes do emit radiation and eventually evaporate. But this created a problem. If stuff falls into a black hole and disappears, what happens to the information it contained? Physics doesn't like losing information. That's like the universe deleting its own save file. So physicists began to suspect that maybe the information about everything that falls into a black hole isn't lost inside, but stored on the surface, like a cosmic hard drive. The 3D content is somehow encoded on a 2D boundary. This was the seed of the holographic principle. Historians still argue whether Bekenstein's area-based entropy was just a clever trick, or the first clue that something deeper was going on. But it gained serious traction in the 1990s thanks to theoretical physicist Juan Maldacena, who proposed a detailed mathematical framework called the ADS/CFT correspondence. Don't worry, we won't make this a math class. Just know that it was the first rigorous proof that a lower dimensional theory could fully describe a higher dimensional space. In other words, a complete universe, including gravity, could be holographically encoded on a surface with one less dimension. Wild, right? Now, our universe isn't quite the kind Maldacena described. It's not shaped like anti-de Sitter space, and we're not made of strings, at least not confirmed ones. But the broader idea that reality as we experience it might be a projection is now considered at least plausible by many physicists. So what does this mean? Well, it means that if the holographic principle is true, then everything you perceive as here, the distance between your hands, the gap between stars, the sense of being in a 3D space, isn't fundamental. It's emergent, a side effect, a projection from a deeper, flatter layer of physics. It's like the universe is a very convincing video game, and we're inside the rendered world. The real data, it lives on the screen, and this brings us back to space. If the universe is a hologram, then the question, does space end or loop, might not even be the right question. Space, in this model, isn't something that stretches or curves. It's a shadow of a deeper truth. The end of space could simply be where the projection stops. Imagine a globe made of swirling light, with all its complexity, planets, galaxies, quantum foam, cast from a thin, distant sheet of encoded data. The map is flat. The world looks round, but it's all illusion, woven together with math. Now for your fringy tidbit of the night. In 2017, scientists at the Fermilab Holometer tried to detect a certain kind of quantum jitter in space that might indicate reality's underlying holographic nature. If space were fundamentally granular, like pixels on a screen, this jitter could reveal the resolution of the universe. The result? No jitter detected yet. But the experiment showed that this wild theory could in principle be testable, which is more than you can say for a lot of cosmic metaphors. And here's the sleepy part. You, sitting there right now, feeling time pass, watching or listening to this story unfold, might just be a three-dimensional expression of a two-dimensional truth. Your hands, your heartbeat, your breath in the quiet. Part of a projected world as convincing as any illusion can be. And if that's true, then the edge of space isn't a place, it's a threshold, between appearance and encoding, between experience and origin. And the loops we imagine in space, they might not be curves through a vast room, they could be feedback in a deeper pattern, a looping sequence in a flattened static image, like a Mobius strip made of code. So does the holographic universe solve the mystery? Not really, but it reframes it. Instead of asking whether space loops or ends, we ask, is space real at all? Is it a canvas? Or just a projection? Are we moving through something? Or are we the motion inside something still? It's not easy to think about. In fact, some physicists consider this line of questioning more metaphysical than physical. But still, it's part of the discussion now. As we dig deeper into the math, we start seeing shadows on the walls, patterns in the noise, a whisper that maybe, just maybe, the universe is faking its own depth. And there's something comforting about that. Because even if it's true, even if you are a projection on a cosmic screen, you're still you, still curious, still real enough to feel wonder. Next, we leave philosophy behind and dive back into what we can see, because space isn't just expanding, it's speeding up, and something out there, something dark, is pushing the universe apart faster and faster. It's time we talked about dark energy. The stars are drifting, slowly, gently, casually coasting away from each other like old friends growing apart after college. But they're not just drifting, they're accelerating. The spaces between galaxies are growing faster with every passing second, like the universe had one too many energy drinks and decided to get weird with its expansion. This isn't a metaphor. The expansion of the universe is speeding up, and nobody knows exactly why. But we gave the cause a name anyway, because that's what humans do when we don't understand something. We call it dark energy, and it makes up about 68% of everything. Let's just sit with that for a second. The thing driving the majority of cosmic expansion, the force dictating the ultimate fate of the universe, is something we can't detect directly. We don't know where it comes from, how it behaves, or even if it's a thing at all. But whatever it is, it's winning. Let's rewind a bit. When Edwin Hubble discovered in the 1920s that galaxies were moving away from us, and the farther away they were, the faster they were receding, it was revolutionary. It gave us the idea of the expanding universe. Most scientists assumed this expansion would gradually slow down, thanks to gravity, like a ball thrown upward, fast at first, then slower, until it either stops or falls back. So for decades, cosmologists debated whether the universe would end in a big crunch, collapsing back on itself, or coast into a slow, cold stillness, a big freeze. Then, in the late 1990s, astronomers studying Type Ia supernovae, those handy bright explosions that act as cosmic mile markers, discovered something deeply weird. The supernovae weren't where they should be. They were too dim, meaning they were farther away than expected, which meant the expansion of the universe had been accelerating. Cue the collective gasp. Historians still argue whether this was the most important cosmological discovery since Hubble's own. Some call it the beginning of a new era in physics. Others call it the beginning of a major headache. Because suddenly the universe wasn't slowing down, it was speeding up, and that meant something had to be pushing it. Something more powerful than gravity. Something invisible. Dark energy. We named it that mostly out of despair. It's dark because we can't see it or touch it. And it's energy because, well, it's doing something energetic. Beyond that, it's a cosmic mystery wrapped in an observational enigma. So what is it? There are a few ideas. One, the cosmological constant. Einstein originally added a term to his equations, lambda, to keep the universe static, since that was the popular belief at the time. When expansion was discovered, he called it his greatest blunder. Fast forward, and physicists realized this constant might actually explain the accelerating universe, a built-in energy of space itself, pushing outward. In this model, every cubic meter of space contains a tiny bit of vacuum energy. As the universe expands, more space appears, and with it, more energy to drive the expansion further. It's a feedback loop, and it doesn't stop. Second quintessence. No, not the magical element from fantasy novels. This version is a hypothetical dynamic field, like dark energy, but changing over time. Unlike the cosmological constant, quintessence could get stronger or weaker, potentially allowing the universe's fate to shift. It could even decay entirely, letting gravity win again someday. 3. Modified gravity. What if dark energy doesn't exist at all? What if gravity just behaves differently on cosmological scales? Some theories suggest that the laws of general relativity might need tweaking. Maybe gravity isn't weakening, it's bending the rules, like that one friend who plays Monopoly a little differently. So far though, observations seem to support a cosmological constant, at least within current measurement limits, but the jury is still out and the tension is rising. Here's your fringy tidbit of the night. There's something called the Hubble tension, a discrepancy between two ways of measuring how fast the universe is expanding. One method looks at nearby objects like supernovae, the other looks at the early universe, like the cosmic microwave background, and they don't agree. The numbers are off, slightly but persistently. Some physicists think this is just a data problem. Others think it's evidence of new physics, possibly even a clue that dark energy is changing, evolving, maybe even temporary. So what does this have to do with whether space ends or loops? Well, dark energy determines how space behaves over time. If it stays constant, space will keep stretching forever, faster and faster. Galaxies will drift out of sight. The night sky will go dark. In trillions of years, observers, if any remain, will see nothing but a lonely galaxy, unaware the universe was ever bigger. But if dark energy increases over time, we could get the Big Rip, a worst-case scenario where the expansion becomes so violent that it eventually tears galaxies apart, then stars, then atoms, then the very fabric of space-time. Space doesn't just end, it disintegrates. Conversely, if dark energy weakens or reverses, gravity could pull everything back for a big crunch, or a big bounce, leading to another cycle. In each of these outcomes, space behaves differently. It could stretch to infinity, or it could collapse back on itself, or it could ripple in cycles like breathing. So maybe the end of space isn't a wall or a loop. Maybe it's a trajectory, written in the invisible ink of dark energy. And here's something hauntingly beautiful. If dark energy is a property of space itself, then every cubic centimetre of empty space is filled with it. Even the vacuum isn't truly empty. It has a kind of pressure, a presence, which means even the silence between stars is alive with potential. Right now, the balance between gravity and dark energy is what shapes our future. If dark energy continues to dominate, galaxies will vanish from our view. Not because they stop existing, but because their light can't reach us. The space between us stretches too quickly. The universe becomes a lonely island. But for now, we're in a golden window. The stars are still visible, galaxies still shine. The great expansion still includes us. Next, we follow this expansion to its weirdest conclusion. What if the universe never truly ends? Because it repeats forever. The universe expands, galaxies drift, stars dim. And somewhere, in the slow cosmic hum of it all, a whisper begins to echo. Not from the past, but from the last time this happened. Yes, tonight we're opening one of the strangest, oldest doors in the universe. What if it all just repeats? What if the universe doesn't end in stillness or collapse or shredding entropy, but instead starts again, 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 over and over in a cosmic cycle so long, you'd never notice it unless you had a memory older than time itself. Welcome to the realm of the eternal return. It's an idea that shows up everywhere, from ancient myth to cutting-edge physics, from Hindu cosmology to modern loop quantum gravity. Some say time is a line, others a loop. But here, in this strange little corner of thought, the universe isn't going anywhere new. It's just going in circles. Let's rewind again. In earlier sections, we looked at the Big Bang not as an explosion, but an expansion, a stretching of space from a hot, dense state. But here's the catch. That state might not have been the first. Some cosmological models suggest the universe wasn't born once, but countless times, each birth following a big crunch or a big bounce. The universe expands, slows, collapses, and rebounds, like a heartbeat on a trillion-year cycle, over and over. That's the cyclic model. One version is called the ekpyrotic universe, from a Greek word meaning conflagration or cosmic fire. In this theory, the universe we know is the result of two higher dimensional brains, like giant cosmic membranes colliding. Each collision is a big bang. Then space expands, eventually contracts, and bang, they collide again. The cycle continues. Another version comes from loop quantum cosmology, which tries to merge quantum mechanics with general relativity. In this model, the Big Bang wasn't a beginning at all, it was a bounce. Before the expansion, we know there was a collapse. But quantum effects, which dominated extremely small scales, prevented a singularity. Instead of everything breaking, it bounced into a new expansion. And so, repeat. This isn't just philosophical musing. The math works. Some models even predict that traces of a previous universe could still be imprinted in the cosmic microwave background, as subtle patterns, distortions, or statistical fingerprints. Has anyone found those fingerprints? Not yet, but people are looking. Historians still argue whether the concept of eternal return was meant to be literal or poetic. The Stoics believed in cosmic recurrence, that everything, including your own life, repeats infinitely in the same sequence. In Hindu cosmology, time is divided into kalpas, enormous cycles of creation and destruction, each lasting billions of years. The Norse imagine a world reborn after Ragnarok. Nietzsche, of course, took the idea and turned it into an existential challenge. Would you live your life the same way if you knew you had to live it over and over forever? Modern cosmology doesn't answer that, but it does ask, could the entire universe repeat? If space is finite and time is endless, repetition isn't just possible, it's likely. In a closed system with finite configurations, eventually the system must return to a previous state. This is known as the Poincaré recurrence theorem, and while it was originally applied to particles in a box, some physicists have dared to ask, what if everything is in the box? Here's a wonderfully unhinged thought. If the universe does repeat, it may do so exactly, with the same galaxies, the same stars, the same you, sitting there, blinking slowly as you listen to this same story unfold again. An eternal rerun, the cosmic DVD menu stuck on play all forever. Or maybe it doesn't repeat exactly. Maybe each cycle is slightly different, like echoing ripples that lose a bit of definition with each wave. Maybe you're still you, but the stars are in different places. Your cat's name is different. Pineapple on pizza is finally illegal. And here's a curious fringe tidbit. The physicist Roger Penrose proposed a model called conformal cyclic cosmology, CCC, where each universe ends in such an empty, stretched-out state that it becomes indistinguishable from the hot, dense conditions of a new Big Bang. The end becomes the beginning, not through a bounce, but through a kind of geometric transition. In 330, space and time don't loop in a literal circle, but one conforms into the other, like flipping a sock inside out and calling it new. Weird? Absolutely, but strangely elegant. Now let's ask, what does this mean for the edge of space? If the universe repeats, then maybe there is no final edge, just a pivot point. The end isn't a boundary, it's a reversal, a shift. The arrow of time doesn't stop, it curves back into itself. The end of space becomes the seed of new space again and again, like a phoenix that rises not from ashes, but from its own exhaustion. But this raises a haunting thought. If the universe repeats, do you? Are you destined to relive every moment, every choice, every mistake, every triumph, every time you left your coffee on the roof of your car? Does every version of you always reach this moment, right now, hearing this same sentence in every cycle? Or is this the only time? If the universe loops but entropy still increases in each cycle, then maybe no two iterations are identical. Maybe each version of you thinks it's the first, the only, the original. But none of you are. You're all echoes of echoes, cosmic reruns with slightly different lighting. But, and here's where it gets oddly peaceful, it doesn't really matter. Because in a repeating universe, nothing is ever truly lost. The stars that die will rise again. The atoms in your hand will eventually reassemble. Maybe not here, maybe not you, but the music of matter will play again. The universe forgets nothing, it just remixes. So, does space end? Not in this model. It curves, it collapses, it fades, and then it wakes up again. Next, we explore where these cycles, and maybe all time, eventually lead. What happens when everything winds down? Do we face a cold, silent heat death? Or is there room yet for a final act? Let's look at the real endings of the universe next. So here you are. After countless galaxies, expanding space, speculative loops, dark energy plot twists, and possible cosmic reruns, you float now at the edge of endings, not the edge of space, the edge of everything. This is where it all winds down. This is where the universe says, "I'm tired," and lies down for a nap that never ends. This is the land of cosmic finales. And depending on which theory wins, it could all end in fire, in ice, or in a kind of mathematical whisper so faint, no one would notice it happen. Tonight we're diving into the most unsettling possibilities, the fates of the universe. Because eventually space will decide what to do with itself. Let's start with the most popular and probably the most depressing model, the heat death of the universe. Despite its name, heat death isn't hot. Quite the opposite. It's cold, utterly, cosmically cold. Here's the idea. As the universe expands, stars burn through their fuel, galaxies spread further apart. Eventually star formation stops, black holes evaporate, matter itself decays, and what's left? A thin soup of particles spread so far apart they never meet again. Maximum entropy, zero usable energy, no complexity, no structure, nothing, just darkness and silence stretching forever. No dramatic explosion, no crunch, just a slow fade into meaninglessness. Historians still argue whether this concept originated with 19th century thermodynamics or later 20th century cosmology, but the core idea is simple. Entropy always wins. And when entropy wins, the universe loses its ability to do anything. It exists, but it doesn't live. Now let's get a little spicier. There's another possible ending called the Big Rip. This one's more exciting, if you're into catastrophic universe-shredding finales. In this scenario, dark energy doesn't just keep expanding space, it accelerates it in a way that becomes unstable. Over time, the expansion rate increases so dramatically that not only do galaxies fly apart, but stars, solar systems, and eventually atoms themselves are pulled to pieces. Even space-time unravels. The whole fabric of the universe just rips. And how fast does this happen? Well, in some models it's still tens of billions of years away, but in others, if the value of dark energy changes unexpectedly, it could be sooner. Don't worry, it's probably not next week. Probably. Then there's the classic scenario, the one cosmologists used to love before dark energy crashed the party, the Big Crunch. In this model, gravity eventually overpowers expansion. The universe slows, then stops, then reverses. Galaxies begin to fall back toward one another. Stars collide, temperatures rise, space collapses inward, and eventually everything compresses back into a hot, dense point. Not unlike how it all began. This could be the seed of a big bounce, as we discussed earlier, a kind of reset button. But it could also be a final collapse. No rebirth, just compression into oblivion. But here's your quirky tidbit for tonight. there's a fringe theory called the Big Slurp. No, really. It's based on the idea that the vacuum state of our universe isn't actually stable. Instead, it might be a false vacuum, a temporary state that only appears stable. But if a more stable vacuum exists somewhere out there, a bubble of true vacuum could randomly form, and when it does, it expands outward at the speed of light, obliterating everything in its path. No warning, no pain, just instant total reset. Vacuum decay, the Big Slurp. It sounds absurd, but the physics checks out. If true, it would be the most abrupt, silent ending imaginable. Like the universe changing the rules mid-sentence and erasing the board before you even knew you were playing. And the weirdest part, it could happen at any time, even now. Still here? Good. Probably just quantum anxiety. Now let's get weird one more time. What if none of these endings are real? What if time itself doesn't stretch forever, but ends? Not because of entropy or vacuum decay, but because time just ends. Some cosmologists suggest time might be a dimension that's only valid within certain boundaries. Once the universe reaches a particular state, be it frozen, collapsed, or fragmented, time no longer has meaning. There's no after. The concept stops applying. In that view, the universe doesn't end. It simply completes. Like a song that finishes. It doesn't crash. It doesn't fade. It just ends. Full stop. That idea has a certain peace to it, doesn't it? But back to our main question. What do these endings tell us about space? Well, they suggest that space might not end with a wall, but with a change in behaviour, with a slowing, a fading, a reversal, or a tear. Maybe space continues forever, but becomes too stretched to hold anything meaningful. Or maybe it folds back in on itself, or collapses, or resets, or reboots. Or maybe it ends by becoming something else entirely, something we can't even define from our current place inside the story. You could argue that space ends when it stops supporting structure, when matter can no longer cluster, when gravity can't pull, when light can't cross the void, when all the rules break or fade and nothing remains but cold distance and quiet math. But here's the beautiful part. We're not there yet. Right now, galaxies still sparkle, stars still fuse, planets still spin, and you, incredibly, are still here, still thinking, still asking. In a universe that may end in silence, your voice is a temporary glorious contradiction, a ripple of complexity in a sea of entropy. So does space end? Maybe not in the way we expect. Maybe it doesn't end with a bang or a wall or even a loop. Maybe it ends with a whimper, a fade, a breath. Or maybe it doesn't end at all. Just transforms. In our final chapter, we'll gather every strange thread from this long, sleepy journey and ask the only question that matters. Does space end or loop back around? Time to decide. So here you are, at the farthest point we can reach. You've glided past the edge of the observable universe, floated through warped space, curved time, looping topologies, ghostly echoes of ancient light, and even the idea that everything, including you, is just a well-rendered illusion projected from the edge of reality. You've been stretched across expanding space, squished into dodecahedrons, bounced through cosmic cycles, and dangled over the void of heat death. You've seen the stars fade, rewound the universe to its first flicker, and pushed against boundaries no eye or probe will ever touch. And now, with every wild theory humming softly behind you like distant stars in a cooling sky, we finally ask, does space ever truly end, or loop back around? The honest answer, we don't know. But let's unravel that gently. Let's start with the observable universe, the bubble around you, about 46 billion light-years in radius, within which light has had time to reach us since the Big Bang. Beyond it, we can't see, not because there's a wall, but because there hasn't been enough time for light to arrive. That's not the edge of the universe, just the limit of what we can see, and that's the first key to understanding the question. Space might not end in a hard boundary, but in a horizon, a kind of fading into unknowability, a limit not of space itself but of access. Imagine sailing across an ocean that curves so gently it seems flat. Eventually the horizon hides everything, but the water continues. You can't see it, but it's there. Maybe forever, maybe not. So is the universe infinite? If it is, then no, it doesn't end. It never loops. It simply goes on. More galaxies, more space, maybe even infinite copies of you, eating infinite bowls of cereal, wondering if they're also a simulation. Some cosmological models support this. An infinite flat space. No curvature, no loop, just endless expansion. But then again, we don't know that space is infinite. It could be finite but unbounded. A space like the surface of a sphere. Travel far enough in one direction, and you eventually return to your starting point without ever hitting a wall. That's a loop. Not in time, but in space itself. The math allows for this. Certain topologies like the 3 torus or the dodecahedral space we explored earlier suggest the universe may wrap around in multiple directions. If so, it's finite but without an edge. A loop not in the science fiction sense, but in the elegant, terrifyingly large sense. And still others suggest space might be finite and bounded, with some kind of literal edge, a boundary, a place where space stops. But this idea runs into problems. What lies beyond the edge? Another space? Nothingness? A giant do not enter sign. Physics doesn't like edges. They make equations grumpy. Which is why most cosmologists lean toward one of the first two, infinite or finite and looped. But then we have the strange newcomers, the holographic principle and quantum cosmology models, where space isn't fundamental at all. In those cases, the question, does space end, becomes meaningless. Space is a construct, an emergent behaviour, a stage, not a thing. There's no ending to space because space isn't a persistent entity. It's an effect. So maybe space neither ends nor loops. It just fades as the simulation loses resolution at the edges of existence. And here's the twist. Even if the universe does loop, we may never know it. If the loop is larger than the observable universe, we won't see repeated galaxies. We won't detect matching patterns in the sky. The universe could already be curled around itself like a snake eating its own tail, and we'd be none the wiser. So which one is it? A looping dodecahedron? An infinite sheet? A bubble expanding on the surface of something else? A 2D projection with 3D vibes? Or a cyclical system doomed to repeat its own mistakes forever? You've seen the evidence, the weird math, the lingering fingerprints, the light from the baby universe whispering from 13.8 billion years ago. Some of it supports flatness, some of it hints at curves, some of it points toward a loop too large to confirm. Historians still argue whether we're even asking the question in a way the universe can answer. Maybe we're not built to understand infinity. Maybe space is playing a game we can't win, with rules we can't see. But here's something gentle to hold on to as the universe keeps doing whatever it's doing. Even if space ends, there's something after it. A question, a concept, a mystery, a next thing. And if space loops, there's something behind you, a past, a story, a pattern repeating like a lullaby in the dark. Whether space ends in silence or circles, you are here, watching, listening, wondering. You're part of this experiment called reality, part of the loop, part of the edge, part of the tiny moment in time where stars still burn and questions still echo, and that makes you infinite in a way. So, does space ever truly end? We may never know for sure, but wherever it goes, forward, back, or nowhere at all, You're already floating through it, comfortable, curious, a little sleepy, and absolutely miraculous. Sleep well, stargazer.